In the name of Almighty God, I am Mahsa Sankoshi, and today I want to talk about thermal X-rays breaking out from the pre-explosion ejecta of a dying massive star. Today I want to talk about a mm, high signal-to-noise ratio optical spectrum was obtained on 2026 April 6 using the Force 2 focal reducer and low dispersion spectrograph 2 instrument mounted on the 8.2 meter Very Large Telescope (VLT) UT1 antenna at ESO's Paranal Observatory. We utilized the 300-volt Griezmann in combination with a 1-second slit, providing wavelength range of 3,410 to 9,330 observations were carried out in the polarimetric multi-object spectroscopy (PMOS) mode. 8 integrations were obtained, each with an exposure time of 480 seconds. We processed the raw data collected at each retarder plate angle and extracted the ordinary and extraordinary beams using standard methods in IRAF. Wavelength calibration was conducted with a root mean square accuracy of 0.2. Details of the force 2 per PMOS data reduction and the derivation of the Stokes parameters can be found in the force 2 spectral polarimetry cookbook and reflex tutorial and references. Following the procedures described in reference 80, it is clear that there are no N2 emission lines in the spectral sequence, while prominent Balmer and helium-1 emission lines are present, which reveals that SN 2026 JZF is located at the place of extremely low metallicity. And interestingly, the survey images from Pan-SCR S and the legacy survey show that the location of SN 2026 GZF is on top of a bright blue knot of the host galaxy, indicating that the SN 2026 GZF location is actually very close to highly star-forming regions. Now I want to go to the supernova bolometric light curve. A bolometric light curve for supernova was constructed using a Knot and Sean spectra combined with multi-band photometry from ALT, GRIZ bands, and Mephisto U-Z bands. Utilizing temporal interpolation where necessary. Spectral fluxes were scaled to match the multiband photometry when available. These were complemented by effective fluxes at 3,460 from the Mephisto U band and those at 12,200 from the ALTJ band. Before integration, the spectra were extrapolated to assume zero flux points as 3,000 and 13,500 by comparing the spectral energy distribution set of the multiband photometry before and after host galaxy subtraction. We estimate a host contribution of 2.5 plus negative 0.7 multiplied by 10 to the power of minus 13 ergs per seconds square centimeter, which represent approximately 8% up to 20% of the total flux depending on the epoch. This contribution was then subtracted from the spectral integrated bolometric fluxes. Galactic and host galaxy readings were not taken into account as their contributions are negligible for this supernova. The results were converted to absolute magnitudes by adopting a distance modulus of micro is equal to 35.0 0.84 magnitude to account for minor epoch differences between the spectroscopic and photometric data. Effective epochs and corresponding uncertainties were assigned to each bolometric point. Magnitude uncertainties include contributions from photometric measurements, host galaxy subtraction, and spectral flux scaling fixed at 5%. Spectra from days positive 2.7 and positive 4.7 were adopted for epoch positive 2.2 and positive 4.2 days respectively. Similarly, Mephistophotometry from day plus 6.2 was utilized for day plus 4.2 and plus 5.2, while quasi-bolometric magnitudes derived from Hall-subtracted multiband photometric sets generally underestimate the spectra integrated results by 0 up to 0.15 magnitude across most epochs. The discrepancy reaches to 0.3 magnitude at days plus 2.1 and plus 2.7. We conservatively adopted mean values for these two earliest epochs with assigned uncertainties of 0.15 magnitude. The final bolometric light curve converted to the supernova res frame is shown in the right panel of extended data figure. Now I want to go through the SPO from a CSM shell. At the peak timescale of an SPO signal is determined by both photon diffusion and the light travel time. If the peak is dominated by photon diffusion, the peak luminosity is comparable to the instantaneous injected luminosity at the SPO. L peaks is almost equal to 2 PR to the power of 2 SPO rho CSM nu to the power of 3. The diffusion timescale at T differences is equal to kx rho CSM delta r to the power of 2 divided by c is approximately equal to dynamical timescale. T dynamical is equal to delta r divided by nu sh. Both of order TPX, where kx is the opacity, delta r is the width of the material side, the SPO radius between the SPO radius and outer boundary, and c is the speed of light. Thus, the SPO radius can be expressed as RSPO is almost equal to square root of kx LPTPX divided by 2PC nu sh. As described in the main text, the spectra of EP 260-321A suggests thermal-like emission, implying that the shock cannot be far from local thermal equilibrium, which USH is less than 0.1 C. Furthermore, as the SPI emission is powered by the conversion of the kinetic energy of the outer ejecta, the radiated energy places another constraint on the shock velocity. For a typical broken power law structure of the supernova ejectors, the available kinetic energy between the outer ejecta above velocity nu sh can be expressed as energy kinematic is greater than nu sh almost is equal to energy kinematic parentheses nu sh divided by nu tr, where nu tr is transition velocity. By equating energy kinematic is greater than nu sh to almost is equal to energy total t x, we obtain this equation. Nu sh is almost equal to 0.09 C energy kinematic divided by 10 to the power of 51 arg to the power of 7 divided by 10 multiplied by m ejection divided by 1 m to the power of minus 1 divided by 2 multiplied by etx divided by 10 to the power of 48 arg to the power of minus 1 divided by 5, where MAJ and energy kinematic are the total mass and the kinetic energy of the supernova ejecta respectively. Figure 6 illustrates spectral evolution and volumetric light curve of SN2026GZF. The spectrum integrated absolute volumetric magnitude of SN2026GZF is represented by solid circles plotted alongside the quasi-bolometric counterparts of the representative normal luminosity, luminous and superluminous stripped envelope supernova relative to the other two supernovae with reported X-ray SPO detections. SN2026GZF rises rapidly to a peak magnitude of M ball is equal to minus 18.6 magnitude, peaking brighter and slightly later than SN2006, but almost 10,000 earlier than the normal luminosity SN 2000 HD. The overall shape of the light curve is similar to that of the well-modeled prototypical broad-line supernova SN 1998 BW, although it peaks earlier, suggesting a somewhat smaller MJA divided by energy value. These properties place SN 2026 GZF among rapidly evolving luminous supernova rather than superluminous ones like PTF 1 RKS. This implies that the shock velocity cannot be very low, even allowing for reasonable variations in energy kinematic and MA ejection. Then SPO reduced, determined by photon diffusion, can be estimated as RSPO is equal to square root cox LP TPX divided by 2 PC nu SH is equal to 270 R and cox divided by 0.2 square centimeter uh, per g to the power of 1 divided by 2 multiplied by LP divided by 10 to the power of 45 multiplied by ERG per s to the power of 1 divided by 2 multiplied by 3px divided by 700s to the power of 1 divided by 2 multiplied by nu sh divided by 0.09 c to the power of minus 1 divided by 2. Alternatively, if the observed peak time scale of the EP26O 321A is attributed to the light travel effect, the corresponding SPO radius is inferred to be RSPO is less than or out is equal to CTPX is equal to 300 R TPX divided by 700S. Thus, both the light travel effect and photon diffusion constraint, the SPO radius of AP26 or 321A to be equal to 300 R. For the light curve and temperature modeling, we then consider radiation mediated shock propagating with a velocity of nu h through a CSM shell confined in a range of the R input is less than R and it is less than R out with a wind-like density profile. Rho CSMR is equal to K to the power multiplied by R to the power of minus 2. The normalization coefficient of the density profile is given by the K is equal to MCSM divided by 4p multiplied by R out minus R input with MCSM representing the CSM shell mass at the moment of the SPO where the time 0 T is equal to 0 is defined. The optical depth outside the SPO radius satisfies the tau T is equal to 0 is almost equal to integral RSPO and the upper boundaries are out. Cox rho CSM derivative of R is equal to cox multiplied by 1 divided by R SPO minus R 1 divided by R out is equal to C divided by nu SH, which is contributed by the unshocked CSM as the shock propagates as well photons trapped in the inner shocked CSM and can gradually diffuse out, thus producing cooling emission. We define the layer of the diffusing shocked CSM with optical depth tau is equal to C divided by nu sh as the breakout shell. Then we calculate the mass m diffuse of the diffusing shocked CSM and the unshocked CSM if the shock has not yet swept up all the CSM outside the breakout shell at different time t. The diffusion of photons for the entire shocked CSM can be determined by the m diffuse is equal to m CSM, thus obtaining a characteristic diffusion timescale T diffusive C for the entire shocked CSM. The initial energy of the breakout shell at time t is given by the energy initial 0 is almost equal to m diffusive and nu sh to the power of 2 divided by 2. Since the CSM is very thin, the internal energy can be approximately treated as constant. For example, initial is almost equal to initial 0, where RSH is less than R out. Once the shocked material expands beyond the outer edge of the CSM, RSH is greater than R out. Adiabatic expansion leads to an evolution of the internal energy as initial is almost equal to R to the power of minus 1. The internal energy can therefore be estimated as E initial is equal to M diffusive nu to the power of 2 R out divided by 2RSH. Then we can model the source luminosity light curve of the cooling emission as L as most equal to when the if the T is less than T diffusive or equal to the T diffusive E initial divided by T plus R out minus R SPO divided by mu SH, and if T is greater than T diffusive C, E initial divided by T diffusive C plus R out minus R SPO divided by nu SH. Here, when we have a T greater than the T diffusive, we have a T diffusive instead of T, where R out minus R SPO divided by nu SH is the diffusion time scale for the breakout shell, and our exponential decline describes the rapid fading after most trapped thermal photons in the shocked CSM have diffused out, followed by radiative and adiabatic cooling. Under a local thermal equilibrium, the temperature is determined by balancing the radiation energy density dominated by the luminosity. Nu is almost equal to L tau divided by C r to the power of 2 with the kinematic energy density. Th is almost equal to U divided by I to the power of 1 divided by 4, where I is radiation constant when the shock velocity nu sh divided by c is greater than 0.05 occurs. There is not enough time to form a local photon electron thermal equilibrium, and the blackbody radiation cannot build up. In such a case, photons and electrons are in Compton equilibrium at a higher temperature T. One can define a thermal coupling coefficient as a ratio of the photon density required for thermal equilibrium to the number of photons produced by free emission over the available photon production timescale in the breakout shell, thereby assessing whether the local thermal equilibrium can be established. If n is less than 1, the radiation is in local thermal equilibrium and the observed temperature is T absolute is equal to Th, while if n is greater than 1, T absolute can be modified by Comptonization as T absolute is equal to Th and to the power of 2 divided by zeta T absolute to the power of 2, where zeta T absolute represents photon reduced at lower frequencies and Comptonized to a temperature of T. In our case, T absolute at the early cooling phase can exceed in the thermal equilibrium temperature Th by a factor of T up to 4, suggesting that the emission is not in full local thermal equilibrium but remains partially thermalized. We therefore define a color correction factor FL cool is equal to T absolute divided by TATH to account for the deviation of the source temperature from the blackbody temperature expected under the complete thermal equilibrium, which is used in the main text. The X-ray spectrum is expected to show a wine peak and is conventionally approximated as a diluted blackbody spectrum characterized by T-observer modeling the X-ray light care, an assumption that is also supported by the observed spectral properties of the EP26 or 321A. The observed light care and temperature are modified by the geometric light travel time effect, whereby photons emitted simultaneously from the different locations on a spherical surface reach the observer at different times. Then we use this model to simultaneously fit the X-ray light care and temperature of EP260 to 321A with a total of five free parameters: outer boundary R out ratio between inner and outer boundary R in divided by R out shock dimensionless velocity zeta sh is equal to mu sh divided by c CSM mass MCSM and time of shock breakout relative to the first observed data point. First, we perform Markov chain Monte Carlo fitting with MC to model the X-ray light curve and temperature of EP or Einstein probability 260 321A with the resulting fits shown in figure 1. The median values with the 1 sigma regions of the key parameters are out is equal to 324.5, and R in divided by R out is equal to 0.807, corresponding to R in is equal to 261.7, and zeta sh is equal to 0.0894. Logarithm 10 MCSN divided by m is equal to minus 3.88, and the time of first is equal to 142 minus 1. Now I want to go through the supernova light curve modeling. The fitting result presented in figure 4 suggests that the traditional radioactive model can provide a plausible explanation for its N2026 JZF, but a high nickel to ejecta mass ratio and extreme nickel 56 mixing are required, which somewhat reduces the feasibility of the model. Therefore, here we try to model supernova in alternative scenarios, in particular by invoking other energy sources, as usually suggested for unusual for supernova phenomena. A powerful central engine, for example, millisecond magnetar, could be formed in SN 2026 GZF, injecting energy into supernova ejecta during its spin down. In our calculations as well for the radioactive model, the monochromatic luminosities in different filters are obtained by considering blackbody spectra for the supernova emission. However, for short wavelength emission, for example, Mephisto nu, Mephisto U, Mephisto and U, and additional phenomenological suppression factors such as FAUV, ultraviolet is equal to minimum of 1 lambda res divided by 4500 to the power of 3 is invoked to match the observational data where lambda res is the res frame wavelength of each filter. The fitting result which a magnetar engine are shown in the extended data figure 7 as shown. The shallow increase of SN 2026 GZF has been well explained because T to the power of minus 2 behavior of the energy released from the magnetar naturally determines a logarithmic increase. Moreover, the inferred parameter values are also consistent with previous work for the other SN nickel ICBL in the magnetar engine model. Nevertheless, in order to account for the detail of the supernova emission, 0.26 m of nickel 56 is still required. In addition, owing to the potentially complicated CSM environment, one may suggest that SN 2026 GZF is powered by an interaction of the supernova ejecta with the CSM. However, this model inevitably requires the presence of a highly optically thick CSM shell, which would determine a large optical depth for the soft X-rays due to photoionization or electron scattering, and thus can in principle obscure the previous SPO X-ray emission. In principle, the potential anisotropy of the supernova explosion could still help circumvent this difficulty. The more serious challenge to the CSM interaction model is that it is actually difficult for the nearly static CSM to generate sufficiently broad lines to match the spectral observation of SN 2026 GZF. The optical data at less than 10 to the power of 4 always exceed the supernova emission regardless of the power scenario. The empirical blackbody fit of the early data gives a blackbody radius almost equal to 5 multiplied by 10 to the power of 14 centimeter. This makes it difficult to explain which with the supernova emission as well as the cooling of the SPO, no matter which energy mechanism is invoked. Alternatively, this early optical bump is likely to arise from another emission region, which is of a translativistic velocity. Here, we tentatively describe the early optical emission by using an evolving blackbody component parameterized as TBB is equal to T0T divided by T reference to the power of minus alpha T. UAT is equal to tau beta is equal to U0 T divided by T reference to the power of minus alpha U, where the dynamical time T is defined to relate to the observer's time T by T is equal to T divided by 1 plus Z multiplied by 1 minus zeta plus 1 minus zeta ejection divided by 1 minus zeta RSPO divided by nu ejection. The best fit as presented by the dashed line in the extended data figure 7 gives U0 is almost equal to 0.89, alpha U is almost equal to 0.14, temperature 0 or temperature initial is equal to 1.83 multiplied by 10 to the power of 4 Kelvin, and alpha T is equal to 0.61 for T reference is equal to 10 to the power of 4, corresponding to zeta is equal to 0.67, and tau is equal to 1.34 at T reference is equal to 10 to the power of 4 second. Here, the Mephisto nu band obviously cannot be included by the blackbody description. This fitting result implies that the sub-relativistic cocoon could provide a plausible explanation for the early optical boom, as the boom must not be accounted for by the late cooling of the non-relativistic SPO. A powerful central ING, as suggested above, may help to understand the existence of such a sub-relativistic cocoon, since a relativistic jet can be driven by the engine even though the jet is finally choked in the progenitor. You see that we have figure 7, and the y-axis we have an apparent magnitude plus offset between the 28 to 12 multiplied by mm, its offset of the y-axis, and in the time since which is applied in the x-axis, we have from the 1000 up to the 10 to the power of 6 seconds. Figure 7 shows a fit of the SN 2026 GZF with a magnetar engine. The solid lines give the theoretical light curves from the magnetar engine model for the following parameters: initial spin period pi is equal to 1.60 millisecond dipolar magnetic field strength. BAP is equal to 4.39 multiplied by 10 to the power of 15 G. Ejector mass is equal to 2.38, and nickel 56 mass 0.26 and kinetic energy 2.48 multiplied by 10 to the power of 51 R. The dashed light colors are obtained by assuming blackbody emission with an empirical power law, evolving temperature, and photospheric radius. Now I want to go to the radio observations and constraints. We compile radio follow-up observations of Einstein probability 260 321 ASN 2026 GZF from our collaboration and public GCN circulars as summarized in extended data table. 5 time are measured relative to the WXT onset. T0 is equal to 2026 the March 21st at a time of 12:16 based on the UTC. For observations with reported time range, the listed epoch is the midpoint of the interval. The observations cover zero point 0.7 up to 23 gigahertz from Point one, 5.1 to 31.1 D after T0, non-secure radio counterparts detected upper limits were measured from the local root mean square (RMS) at the optical position of SN 2026 GZF in the final image. Meerkat observations at 1.3028 and 3 GHz were reduced with the OX cut pipeline, while at ATCA observations were calibrated and imaged with standard CASAR procedures. The UGMRT Band 5 publication non-detection was reduced with the SPAM pipeline as reported in GCN 44,227 based on the reference 91 Merlin 5 GHz C-band observations, reducing CASA with the Merlin pipeline. Also yielded non-detections at T absolute is equal to 13.489 and 30.989 D with RMS values of 22 and 12 microjoule Y per beam and corresponding 5 sigma limits of less than 110 and less than 60 microjoule Y per beam, respectively. Public VLA and ATCA constraints are included from GCN circulars. A low significance VLA feature reported at 13.6D is not considered a reliable counterpart after subsequent follow-up reinspection, revealing no significant variability. These limits are presented in extended data figure 8 can provide a useful constraint on the radio emission arising from the interactions of supernova objects and in particular relativistic jet with CSM. We further examined the radio constraints by comparing two representative external shock processes which arise from the propagation of supernova ejecta of GRB-like relativistic jet into a wine-like CSM. In both scenarios, the density profile of the wine-like CSM is assumed to be rho is equal to R to the power of minus 2, with the normalization I star is almost equal to R divided by 5 multiplied by 10 to the power of 11 G per centimeter, where ISO is equal to 1 approximately corresponds to m is equal to 10 to the power of minus 5 y r to the power of minus 1 for a new W is equal to 1000 km per second. Specifically for the supernova radio emission, we varied the ejecta velocity over Betsa ejection is equal to V nu ejection divided by C belongs to 0.03 to 0.08 together with the microphysical parameters logarithm epsilon E belongs to minus 1.75 up to minus 0.25 and logarithm epsilon b belongs to minus 2 up to minus 1 for the jet. After Galois emission, we scan the initial Lorentz factor tau 0 belongs to 10 to 300. The isotropic equivalent kinetic energy logarithm E energy isotropic based on the ERG belongs to 51 up to 53. Logarithm epsilon E belongs to minus 1.25 up to minus 0.25, and logarithm epsilon B belongs to minus 4 up to minus 0.5. For each scenario, 10 to the power of 4 parameter combinations were sampled. The shaded regions in extended data figure A show the one epsilon range of the predicted flux density at each time or frequency of observation, while the solid and dashed curves denoted the representative curves. To be specific, the representative parameter values are taken as tau 0 is equal to 100, E isotropic is equal to 10 to the power of 52 ARG, epsilon E is equal to 0.1, epsilon B is equal to 0.01 for the jet external shock, which are broadly consistent with GRB after glow observations, while for the supernova external shock, the adopted zeta ejection is equal to 0.1, epsilon E is equal to 0.1, epsilon b is equal to 0.1 based on the references 23, 98, 99. The observed radio upper limits are consistent with the low fluxes expected from the ejector CSM interaction. Contrast standard energetic GRB light after the low in a comparable wind environment would generally produce substantially brighter radio emission and can exceed the observational limits or broad region of the scan parameter space. These radio non-detections therefore disfavor the presence of a luminous on-axis GRB-like relativistic jet associated with Einstein probability 26 0 321A based on the SN 2026 GZF. However, they should not be interpreted as ruling out all possible relativistic or engine-derived outflows, such as an off-axis jet of a viewing angle theta v is greater than 45 degrees, and in particular the deeply shocked jet. As a result, a weak subrelativistic cocoon could appear on the line of the sight, which contributes to radio emission of flux of Fa nu is equal to 1.8 multiplied by 10 to the power of minus 5 meter joule by beta divided by 0.6 to the power of 31 divided by 4 T absolute divided by 10 days to the power of 3, and nu divided by 10 gigahertz, where p is equal to 2.5, epsilon e is equal to 0.1, and epsilon b is equal to 0.01 are adopted, and typical density of n is equal to 1 um, per cubic centimeter is used because the cocoon has moved into the interstellar medium rather than staying in the vine like CSM. Obviously, this flux is safely below the current upper limit for fiducial parameters. Figure 8 illustrates radio upper limits downward triangles compared with model predictions. Left for radio light curves at 1.25, 6, 17, and 23 GHz shown as a function of time. Since T0 solid curves illustrate expected emission from supernova ejected CSM interaction, while dash curves indicate the radio afterglow of axis jets. The shaded regions arise from the typical uncertainties of the model parameters. Right theoretical radio spectra as representative observations epochs of 5.76, 9.15, 22.6, and 31.1 days. Thank you so much for watching my tutorial video until the end. Today is the 24th of June 2026. Time is 2 o'clock in the morning. If there is any simulations for this literature, you can download it from github.com/masterscript, github.com/kashi script, or github.com/safroscript.